we've had a rough go of things. I think the readjustment maybe to being back in school after fall break. I don't know, but maybe he got a bad test grade. He did not. He is.
Which grade is he in?
He's in first grade. He is quite bright, and I don't say that as like a parent who's proud. I mean, like I'm sure I'm plenty proud of him, but he is very smart, and he wants you to know he's very smart. Like it's not always. I said your dad is the smartest person in most rooms he walks into, but he doesn't talk about that. Like that's kind of the way I would like you to handle this.
Yeah, you gotta show it, not
right. Correct. Just do it. Just mind your business and do your thing, and you know.
Yeah. You should tell him people won't think he's smart if he mentions it.
Yes. Well. Anyway, okay. So on Friday, we talked about the definitions of one-to-one and onto. We also started functions, right? Okay. So we did all of this stuff with functions, and then we talked about what it means to be one-to-one and what it means to be onto. This is a weird proportion, isn't it? Oh! Is that better? Not that. Which you want 1610? Okay. So we talked about domain, codomain, range. Codomain is the target, like a whole set. The range is actually the pieces that do get hit. If a function is onto, the codomain and the range are equivalent. The identity function just maps everything to itself. We did these examples. We talked about one-to-one proofs, and we did one of them. When you're doing a one-to-one proof, you assume that for some x and some two values in your domain, that their target was the same, that their image is the same, and then you show that the actual elements have to be the same in the domain. That the two targets that landed in the same spot are actually just one dart. Yeah? And we did one proof with that, this one here. So we let f from R to R be a function defined by f of x equals 5x minus 2. Let a and b be in R, our domain, and assume that f of a equals f of b. That means 5a minus 2 equals 5b minus 2, so 5a equals 5b, so a equals b. And since a is b, whenever f of a equals f of b, f's 1 to 1. Okay. Do you want to keep writing one-to-one proofs? Do you want to talk about onto proofs? Yeah. All right. So we have this function h from 0 to infinity to the real numbers defined by h of x equals x plus 3 squared plus 12. We want to prove that this function is one-to-one. So, did you say you don't need scratch work for this one? Oh, yeah. Well, I mean, we can do it anyway. So if we let, do you want to call them A and B or X1, X2? Okay. So we're going to let A and B be in our domain. So A and B are in 0 to infinity. And we want to assume that they landed in the same spot. So we're going to assume that H of A equals H of B. And what do we want to show? Yep. Okay, so if we have H of A equals H of B, what does that mean? Yeah, so we're going to do A plus 3 squared plus 12 is equal to B plus 3 squared plus 12. And then we're going to basically solve that like get A and B equal to each other. So subtracting 12 from both sides, you have A plus B 3 squared. My gosh, is B plus 3 squared. Taking square roots here, we don't have to do plus or minus because A and B are both positive. So this is going to be A plus 3 equals B plus 3. This is because A and B are both greater than 0. And then subtracting 3 from both sides, we have A equals B. All right, so we are going to let H from 0 to infinity to the real numbers be a function defined by h of x equals x plus 3 squared plus 12. We are going to let A and B be in our domain, 0 to infinity, and assume h of A equals h of B. I'm basically going to copy my scratch work now. So A plus 3 squared plus 12 is B plus 3 squared plus 12. So A plus 3 squared equals B plus 3 squared, which is A plus 3 equals B plus 3. I'm going to put over here because A and B are both greater than 0. And then write that A equals B. And then my last sentence would be something like, since A equals B, whenever h of A equals h of B, we have shown h is 1 to 1. Any questions about that one? You have like 3 of those on your homework, I think. 4, 5, 6. Yeah. So, sorry, I said a lot of things that don't make sense there. You do have 3 on your homework. Numbers 4 and 5 and 9 are proving 1-to-1 stuff. You have to figure it out on 8, but you don't have to do proof. So, yes. Alrighty then. That paper feels very thin, right? Like thinner than normal paper. I wonder why. Does it not? Really? Okay. Maybe I'm just very strong with this hand. It's thinner. It is thinner. Janiyah and I are right, and the rest of you are wrong. Okay. Can you formally prove that? No. Give me a measuring tape. Okay, number 2, we're done with. Can we scooch back up here and talk about onto proofs? Okay, so what does it mean for a thing to be onto? If we go back to our definition way up here, a function f is surjective or onto, provided that for all y and y there exists an x in x such that f of x equals y. So every element in the codomain is an output of F. So if you have F going from X to Y, you're going to pick a random Y over here, arbitrary, and show it has a pre-image. In X. We get to construct it most of the time. Now that's kind of weird because we're going to build an X, and you're like, well, have I proven it for everything? Yeah, because your Y is arbitrary. So even if your X depends on that Y, it's okay. So that says construct. Good luck reading it. That doesn't look like construct at all. We shall fix it. Construct. I can spell. Okay, so let us find one and do it. And then we'll just go back and forth. Oh my gosh, is this on your homework? You are welcome. This is one of the problems on your homework. Maybe we should skip that one.
We don't care that it's like not actually a function since it fails the test.
This is not injective. Actually, is it? So it is surjective. We're going to prove that because it goes up and down forever. So it's hitting every real number gets hit by it. Okay. It is one-to-one also. You're going to prove that on your homework as well. Because it doesn't have a bunch of other factors of X, so it looks like X cubed. If you would have to have some like even powers of X added in there to get some dips. Okay, so F from R to R defined by F of X equals X to the fifth plus 1 is on 2. Should we skip this one since it's on your homework? Dang it, that one's on your homework too. Y'all, I must have really been out of it. Boy. Well, at least your homework will be easy to grade. No, I mean, look at it after you write your proof, make sure you did a good job. That would be smart. Let's just go with that. Okay, let's do this. To do on 2 proofs, we're gonna pick a Y in R. This is our codomain. It is arbitrary. And we want to find the X that maps to it. We want to find X in X such that F of X equals Y. R, that X should be an R. You with me? This one. This is in your domain. Okay, so the way that we're going to do this is we're going to build it. So if our Y value is equal to X to the fifth plus 1, what does X have to be? You're going to solve for it. So you're going to move that 1 over. So we're looking at Y minus 1 is X to the fifth. Then we're going to take the fifth root of Y minus 1. That is our X value. You need to check, is this in the domain? Is the fifth root of Y minus 1 a real number? Yes. The odd roots, you can take the odd root of positives or negatives. It doesn't matter. If this was a square root, we'd be in trouble. but it is. And so because we have found an element in the domain that maps to our element that we picked in the range, I mean in codomain, the range equals to codomain, we're done. All right, let's write a proof. Let f from R to R be a function defined by f of x equals x to the fifth plus 1. Let y be an element in our codomain. Suppose x equals the fifth root of y minus 1. Notice x is in our domain. Now, f of x is f of the fifth root of y minus 1, which is equal to the fifth root of y minus 1 to the fifth plus 1. That is y minus 1 plus 1, which is y. So we have found x in R such that f of x equals y. So f is on 2. Ready to try it on the next one? Yes? All right, so we are going to pick y in our target, which is 0 to infinity here. And we want to find an x in R such that y equals f of x. So what are we going to do? We're going to construct that x. And we don't have to use plus or minus because y is positive. Or equal to, yeah. And then once we plug that in, if we did f of x, we would do f of the square root of y, which would be the square root of y squared, so you get y back. Is that okay?
Yeah.
Does this feel wrong? No?
You were saying about the odd and even square roots of things.
Yeah, taking the square roots, taking square roots, you need to be taking square roots of positive numbers to end up with a real number. So this is only going to be a real number because y is greater than or equal to 0.
So if it was negative, it not would be
Not for all of the Y's, so it wouldn't be on 2, yeah. If this was from R to R, it would not be on 2. Because at this point, we wouldn't be able to say that X is in our domain. Because it would not always be. Right? For certain values of Y, specifically negative ones, they wouldn't have a pre-image.
They're imaginary numbers.
If they were imaginary, it would be fine. Well, you would use the complex numbers are real, include imaginary numbers, so you could do that.
I was just wondering the same thing, because all my math classes ignore imaginary numbers, and now they're showing up in chemistry. I'm like, what?
Yeah, there's a whole field of math called complex analysis, which does math with complex numbers. Yeah.
Not this one.
Not this one.
Yeah, I don't know, man.
Not this one.
I don't understand why they're in chemistry.
Yeah,
It's fake science.
fake science.
We don't do alchemy. It's not real.
Okay, so it is that X is in our domain here because our Y value is non-negative, which means the square root will be a real number. Okay,
Yes.
proof. We're going to let F from R to 0 to infinity be a function defined by f of x equals x squared. We are going to let y be an element in 0 to infinity, our codomain. Suppose x equals the square root of y, which means x is in R, our domain, because y is greater than or equal to 0. Notice f of x is equal to f of the square root of y, which is equal to the square root of y squared, which is y. Since we found x in R such that f of x equals y, we have shown f is on 2 or surjective.
If you listen closely, we can learn differential
I
equations.
know. I'm trying not to learn differential equations if I can help it.
I get the cell phone and peek in, so I know.
Do you have any questions about number 2? Do y'all know Maddie Parsons? Do you remember Maddie Parsons? Any of you? She graduated 2 years ago.
She's the person who's running the engineering club.
That was Kira. They graduated at the same time. Yeah.
Yeah, it was like whatever. I mixed them up, but I think
Yeah.
I figured them out.
She is teaching at a high school in Columbia. She's teaching math at a high school in Columbia, and
You go to high school.
Ben Lippin.
I know people who go. Like I have my other brothers know people who go there.
Yeah.
They have really good cross country. Like I know the cross country teams are on it, so.
Mm. It seems oddly culty to me, but you know, whatever. I'm being recorded. Maybe that's why they're so good at cross country.
Yeah.
Used to
They
running.
get a lot of funding.
What was I saying? Oh, she had a parent come and complain to her, like, which is why I'm teaching you all and not teaching high school students, just so you know. Because if your parents walked up to talk to me, I would walk away. I mean, if they were here to yell at me about something, right? I would be like, oh, I'm so sorry, I can't talk to you. What's the FERPA password? I don't know. Okay, so, but she had a parent complain because she teaches, like, with her iPad, like I do. This parent said it would just be better if you wrote on the board. Uh-huh.
Yes.
Except not with my back to you and not standing in front of it, which is better. Yeah. It's really hard to not stand right in front of it. You're always going to be in front of a student. Like, I mean.
Yeah, that's not even infinite space. You don't have to erase.
Right? I wouldn't call it infinite necessarily, but. Yeah. And I am. Anyway, just parents, you know, they find that we all do it. People, we find that one thing to latch on to that's not something we're comfortable with. And I feel like I shouldn't do number 3 for you too, because it is on your homework.
I'll be in office hours anyway.
What if we just did the scratch work for number 3, and then you wrote the proof yourselves later?
Yes.
This is kind of fun because we go from an ordered pair to a value. So we're gonna pick something in the range, a codomain, which is an integer. So we're gonna pick a y value in z, which is our codomain. And we want to find find, whatever. We want a, b, say, whatever, in z cross z, where f of a, b equals y. So what two integers could I subtract and get y? Could I do 2m minus n, 2a minus b, 2 something minus something and get y? I'm trying to fill this in. 2 something minus something gives me y.
2, 1 minus 2.
I got to get y. Should use a y. Use a y.
So we just use
We got to use an ordered pair. So what could we use that involves a y? Y would work, right? 2y minus y is y. You could also use a negative y. So you got options. You can use y. You can use 0, negative y. I can't come up with any more options at the moment. Can't use 1/2 y and 0 because we don't know that 1/2 y would be an integer then. But yeah. And then f of, y would be 2y minus y, which is y. So you found it, you did it. Well, we did. Are we following that or not following that? So you would then write the proof yourselves. Yes? Okay. What one-to-one proofs did we not write? Shall we go look at any of those? Yeah, let's do number 3. Why did I scoot around in these notes so randomly? I really didn't intend to do that. I'm sorry. F from z to z is our function defined by f of n equals n cubed. We want to show that this function is 1-to-1. What does that mean for it to be 1-to-1? Hmm? Every input has exactly one output is the definition of a function.
Every output has one input.
That would be the definition of 1-to-1. Every input has exactly one output, and every output has one input, has an input. Yes? Okay, so anyway. What we want to do then is to look at, we want to let A and B be in our domain. These are 2 darts we have in our hands. We want to assume the place that they landed was the same. And then we want to show that A actually equals B. All right, I'm writing the proof. Let f from z to z be a function defined by f of n equals n cubed. We are going to let A and B be in our domain and assume their image is the same. Assume f of A equals f of B. Then A cubed equals B cubed. So A equals B. I'm not going to do that there. I'm going to do that in a line. And since A equals B, whenever f of A equals f of B, we have that f is 1-to-1. Boy, that was short. How are we doing with that? Good? Okay. Now, I believe we have one more 1-to-1 proof and one more on-to proof to do. Yeah. Okay. Let's do this one-to-one one. Can we do just scratch work? Just scratch work. I'm apparently in a lazy place today. I don't want to write a bunch of proofs. But they're all the same. The structure's all the same. You can do it. Just follow one, right? Okay, so scratch work. We are going to you want to use A, B, C, and D? A and B and C and D be in Z cross Z. So we're picking two elements in our domain. And we are going to assume that the place that they landed is the same. And we want to show that AB equals CD. Okay, so f of AB would be A plus B and then 2A plus B. F of CD would be C plus D and then 2C plus D. Right, we know that those ordered pairs are equivalent. We need to know that if two ordered pairs are equivalent, their pieces are. Does that make sense? So we know that A plus B equals C plus D. Are we going somewhere helpful? Are we?
Do you just know that when we like break it up into two equals or like each side?
Uh-huh. Oh yeah, I said that? No, did I? I don't know. A plus B is equal to C plus D, and 2A plus B is equal to 2C plus D. Because the beginning pieces of the ordered pairs and then the end pieces have to match. But then we have a system of equations that we can solve. I'm going to like subtract this off. So I'm looking at 2A minus A, which is just A, B minus B, which is nothing, 2C minus C, which is C, and D minus D, which is nothing. So we got A equals C. Then A plus B equals C plus D gives A plus B equals A plus D. So B equals D. And then since A is equal to C and B is equal to D, A, B equals C, D. When I wrote this up in my proof, just so y'all know, like this thing, when I did actually in my proof, I put it backwards so that I wasn't like subtracting up. It doesn't matter. But I said something like solving the system and then did the thing. The wording on that could get weird. Okay. That is our last one-to-one proof. Are we okay with that? Do we feel like we understand one-to-one proofs all right? Okay, so let's do this last on to prove. So this is the same function, huh? This is the same function that we just did, but it's not actually on your homework, right? Not that one. But this is the one we just showed, or no? 2m plus n plus n, 2m plus n. We just showed it's 1-to-1. Now we're going to show it's onto. Good? Okay. So we're going to pick, what do we want to call our target ordered pair?
Can't do A, B.
Why? I mean, sure we could.
Let's do A, B.
Okay. So you guys would agree with me that in this like setup, m plus n is A and 2m plus n is B. Okay. I want to use those to get m and n because mn is going to be the place where I started. I want to solve those for m and n in terms of A and B. So n is A minus m. I don't know if this is the best way to do this. This is just how I did this. A minus m is B. So m plus A is B. That means that m is B minus A. And n is A minus B minus A. So n is 2A minus B. So I'm going to have mn is equal to 2A minus B and B minus A. This is my constructed x, if that makes sense. And so then what we would do is f of mn would be f of 2A minus B, B minus A. Oh gosh, I shouldn't have substituted that in yet. I'm not going to. That would be m plus n, sorry, 2m plus n. Goodness. So now I got to do, this would be 2A minus B plus B minus A. And then 2 times m, which is 2A minus B plus n, which is B minus A. Goodness gracious. I'm feeling a little lost in this, but I think I've done everything right so far.
Well, let's see if we get AB. We did, huh? Negative B plus B goes away. 2A minus A is A. Woohoo! I have 4A minus 2B plus B. Uh-oh. Minus A. Did I? Huh? What?
One right above where you were writing,
This one?
the one right after.
This one?
Yes, so M is, B minus A, right? So you substitute that in.
I thought M was 2A minus B. Oh, I did it wrong over here, y'all. I did it wrong over here. I switched these. Look, I did. M should go there and N should go there. M is B minus A. Thanks, Emily. N is 2A minus B. Then M plus N would be B minus A plus 2A minus B. 2M would be 2 times B minus A. There it is. Plus N, which is 2A minus B. Oh, golly. B minus B, negative A plus 2A is regular A. This is 2B minus 2A plus 2A minus B is regular B. Woohoo! All right, what do we think? What do we think? Good? Okay. Any questions about that now? Obviously, I didn't write the proof yet. I didn't. I'm not gonna. I shouldn't have said yet. Yay! Okay. Okay, that is everything up to page 8 then, I believe. And we are really going to talk about a bijection again for just a moment. So the function, there's no exercise here. Whoops. Prove or is, I don't know, something. I should fix this later. Is this function from R to R given by f of x equals 2x plus 1 a bijection? What would it mean to be a bijection? It's both jections. It is injective, so it is 1-to-1, and it is surjective, it is on 2. To do a bijection, it is 2 proofs in 1. A proof that something is bijective is 2 proofs in 1. First, you're going to show it's 1-to-1, and you're going to show it is on 2, and then you're going to say, since f is 1-to-1 and on 2, f is a bijection. We haven't actually written a bijection proof yet, have we? Perhaps we should. I shall write it here. Sorry, I keep changing my mind. This is why I should have prepared for class today. It's fine. What, Brian? I should have. I'm going to have to.
No, I was just looking at that.
I'm going to have to write very small.
Like not to erase.
Let f from R to R be a function defined by f of x equals 2x plus 1. First, let A and B be in R. I'm showing 1 to 1 first. And assume f of A equals f of B. Then 2A plus 1 equals 2B plus 1, and clearly A equals B. Thus, F is 1 to 1. You guys. Soccer team threads. Just awful. Parents. They're very competitive, and also, like, I don't know, look at the schedule yourself. Why you have to ask the coach every time we have a game or practice? Practice is every time the same. Why are you asking?
When's the next class?
Right. When does this class meet?
If this class was meeting right now, I'd be here, but.
And it's like, you have his phone number. Just text him. Why are you texting all of us? I don't know. I don't need to know that you don't know when our games are.
He's bringing this next this one.
That's the thing. He says, like, we'll have a game today. Thanks so-and-so for signing up for snaps. Like, that's the sort of reminder we need. Not like, coach, when's the game?
Do we need to bring our hats?
Right. What color are we wearing this week?
It's gonna rain tomorrow.
Right.
Let's practice tonight.
Should we practice? Okay, F is 1 to 1. Then we're going to show it is on 2. So we are going to, I'm going to have to do some scratch work in a moment, but whatever. Now we are going to let Y be an element in the codomain. That was supposed to be a parenthesis, but it has turned into a C. It's fine. Codomain. All right, if Y is equal to 2x plus 1, what is X? Y minus 1 over 2. And is that a real number? Is that in our domain? Yes. So we're good. Right, if these were integers, guys, we'd be in trouble. Right? Yes. Yeah, because if Y was even, if Y was even, then it would not be, so if Y was, I don't know, 2, right? Then X would be 1/2, and X wouldn't be an integer. So you would have found something that doesn't have a preimage in the domain. Does that make sense? So every time you want to check, is this thing actually, this X I constructed, is it actually in the domain? If not, the function's not on 2. Because you found one, but it wouldn't work. Okay, we'll talk through that in just a second when we do this. Okay, so we are going to let Y be in R, the codomain, and assume that, that X is equal to Y minus 1 over 2. Notice F of X equals F of Y minus 1 over 2, which is equal to 2 times Y minus 1 over 2 plus 1, which is Y minus 1 plus 1, which is Y. Ugh, I wish that hadn't taken up all that space. Darn aligned equal signs. You know how much space I could save if I could just write them horizontally? Lots. Too bad. Right. Trees are already dead. All right. And then you would say something like, since we found X in R such that f of x equals y, f is onto. Since f is 1-to-1 and onto, it is a bijection. Questions about exercise number 6? We're feeling okay? All right, 1-to-1 and onto proofs. To show a function is 1-to-1, you are going to let A and B, that's let A and B be in your domain. Assume f of A equals f of B. Show A equals B. How would you show a function is not 1-to-1? Yeah, you would find an example. So find A, B, and X where f of A equals f of B, but A does not equal B. Like x squared, right? You would do -2 and +2. F of -2 and f of +2 would both be 4, but -2 doesn't equal 2. Does that make sense? Okay. How do you show that f is onto? We're going to pick a y, arbitrary, pick y in y, and show there exists an x in x where f of x equals y. You have to build that x. You're going to construct that x based on your y. Now, how would you show that something is not onto? Yeah, you would show that you would find a y in y that doesn't have a preimage. Find y in y with no such x. Like on that one, if f was going from z to z, and f of x was 2x plus 1. 1, 2 has no preimage. Like 2 equals 2x plus 1, you would subtract, you would get that x is 1/2. And that's not an integer, so its preimage is outside of the domain. All right, to show a function is a bijection, you want to show that it is both 1-to-1 and onto. Okay. 1-to-1 and onto, that is that. Do you guys have any questions about 7.1 or 7.2? No? The very end of this is about being invertible. For functions to be invertible, they have to be 1-to-1 and onto. And like college algebra or whatever, we really only talk about it being 1-to-1, passing the horizontal line test, so that when we invert it, it passes the vertical line test and still is a function, right? Yes. So it does need to be a 1-to-1 correspondence, so it needs to be 1-to-1 and onto. We don't usually distinguish about the domain versus, the codomain and the range yet in college algebra. That's why we don't talk about onto. Good? Okay. It's invertible if when you compose it with its inverse, you get the thing back. So f of f inverse of y is y and f inverse of f of x is x. This is perhaps out of order too because I'm about to talk to you about what compositions are. So we'll go ahead and just move this somewhere else later. So the question would be on these things, let's like determine if these are invertible. F from R to R given by f of x equals x squared, is that invertible? Does it have an inverse that is also a function? No! Well, it would be the square root of x, right? Square root of x is real as long as x is positive, right? Yeah. This is a very helpful sheet of paper here. This thing is not one-to-one or onto, so it's not invertible. It is, this, so it's not one-to-one anywhere. And because you've got both of these halves, it's also not, you have these halves. Let me work that again. This is x squared. Because you have both halves, it's not one-to-one. Yes, because this thing doesn't extend to the floor, it's not onto. Because we're trying to get to all of the real numbers. So any negative real number does not have a pre-image in this thing, because that would be complex. Okay, how about going from 0 to infinity to 0 to infinity with that same function? Yeah, it is. This one fixes both of those issues. F inverse of x would be the square root of x. All right, so f is a function on this one that takes ABC to 1, 2, 3. Oh. Okay, some function f. F takes A to 2, B to 1, and C to 3. Is f invertible? Yes, it is one-to-one and it is onto. Everything gets hit on the right. Everything only gets hit once on the right. Okay. Good to keep going? If I am? Sweet! Composition of functions. I would keep talking to you guys for like the next, I don't know. If I didn't need to pee, I could go longer, but an hour and 20 minutes is a long time. Yeah. Okay. F goes from x to y, g goes from y to z. These are functions. A new function g of f that goes from x to z can be defined like this for all x and g. I will tell you guys, students often screw this up because you're reading that g first, so you think it's the first one, and it's not. The inside stuff happens first, so the f happens first and then the g. Okay, so what we want to do is we are going to draw some bubble diagrams that are compositions of functions and that fit these things, which is kind of fun. You ready? So we're going to have 3 bubbles, x, y, and z. And they're going to be so good. Look at them. Look at them. Just beautiful. X and y and z. And for this composition of functions, we're looking at g of f. So f is the first function that happens. G is the second function that happens. Okay, so we want to be able to draw this thing where f, that first one, is surjective or onto. But overall, because this is g of f, it goes from x to z. Where that is not onto. So F is on 2, but the whole thing is not. Y'all are like, what are we supposed to be doing? We're going to put some stuff here. Like this would make F on 2. You agree with me? But if I want the whole thing to not be on 2, I'm just going to make that second part not be on 2. Because then this, let's call it C, I don't know, has no preimage under G of F. Good? I'm going to have to make that be smaller. Why are my bubbles so big? They're taking up the whole space. Whatever. This is F again, and G. This bigger thing is G of F. I want to know where G is on 2, but the whole thing is not. In which one?
Three dots in X, 2 dots in Y, and 2 dots in Z.
So I think if we do that the other way, yes. If we do 3 in these two, then I do have to put this somewhere. So making it not go to that third thing is good. I guess it wouldn't matter if you did make it go to the third thing, because in the composition it still wouldn't go anywhere. Hey, that's what I did on my example. I did send that third one to the third spot. But. Okay, number 3, F is injective, but G of F is not. So F is 1-to-1, but the big function isn't the composition. So F again is that first one. G is the second one. Composition here is G of F. See, I did it. We want where F is 1-to-1, but G of F is not. 2-2-1. So F is 1-to-1, but both, whatever these are, say 1 and 2, would map to C in the composition. Oh, I gotta send this somewhere. My bad. Now they will actually both map to C. So the preimage of C under the whole function, the big function, would be 1 and 2, not just one of them. Yeah? So they were actually different darts, not the same dart. Does that make sense or no? Okay. Number 4, G is injective, so G is 1-to-1, but the overall function is not. The composition is not. What about 3-2-2? Huh? Yeah. That was a silly little horn. Do you think that was on a car? Maybe it was just that student. Okay. Any questions about these? These are good examples. And then we have a whole bunch of proofs to write.
I like this.
Do you like the bubbles?
Yeah.
I call these, my teacher called these potato diagrams because they look like potatoes. Eunice, we are thinking that homework's due on Friday. And we did some of it today in class. Also, we have at least 2 students signed up for tutoring this afternoon.